So there's a very specific trick involved when you're solving Sec³. And if you haven't watched a video on how to solve Sec⁻x, you need to watch that first because Sec³ gets reduced to integral of Sec⁻x. So, but if you're doing this one day before exam, I will include the PDF here. But the specific trick that you need to know with this example is that on the right side, you get another Sec⁻x. And that is back to square one because that's what you started solving, right? So the way that you approach that problem is no different than how you approach this sort of problem if you had x on both sides of the expression. You move it over the bridge, which is the equal sign, and obviously the sign changes. And that is no different. The expression, the same expression as on the left side and on the right side. So you just move that over to the left side, and then obviously they asked you for 1 Sec⁻x, not 2, so you divide your answer by 2, and that's the trick. We're gonna use, integration by parts. I'm gonna write it down here. And you're probably thinking, well, I still need to choose u with integration by parts, and you do. And this is usually a very useful acronym to determine what your u should be. However, unfortunately, it's not useful in this case because there's only one function here. I'm going to rewrite this as the product of 1 secant and secant squared dx. And I'm also going to tell you the most important part of solving this problem is at this step, I think at least, because after this, a lot of the important decisions are made for you, so you just follow the process after this. And I like to use this really nice template. So what this template is telling you is that, well, this is, up until here is the problem that's given to you, right? What this template is telling you is that you have u, but v and du, you don't. So first step of solving a integration by parts is finding v and finding du. All right, so for this, you have to take derivative of secant, right? And if you don't remember that, you kind of need to for this example. I'm gonna have it here so that you can look at it. So derivative of secant, you can remember it like this, that secant always brings its best friend tangent with it, and that's dx. All right. So we found du, so I'm immediately going to write it here in its corresponding bucket. Okay, now we need v, and getting v is always a bit trickier because to get v from dv, which is given to you, you have to take integral, right? So you put integral here, integral of dv is simply v, right? Because integral of dx is simply x. And integral of secant square x is, I want you to look here. Integration, indefinite integral, is also called anti-differentiation because it is antiderivative. And if you can think of a function whose derivative is secant square, well then you have your answer to integral of secant square x, and that is tangent x. And if you're unsure, you can take derivative of this, and that will give you secant square x back, right? So you know you can always check your work with integrals, because if you take derivative and get the original function back, you know you did it right. At this point, I have all the ingredients that I need. All right, so this part is simply uv, and this is my integral, right, which is right here. All right, I'm going to rewrite it without the buckets like a normal integral and try to solve it. All right, so I'm going to rewrite this. Notice that I have this twice, so that's simply tangent square x and 1 secant x dx. All right, so now I'm going to use trig substitution of tangent square x. If you don't remember what that equals to, it comes from this formula right here, which is basically Pythagorean theorem said in the language of trigonometry. It's the same thing here because you assign it like that. It comes from this triangle, right? And if you follow these transformations and just do algebra here, you get this trig identity. A lot of trig identities come from this relationship right here. So that's exactly what I'm going to use and substitute tangent square x with tangent square x with secant square minus 1 right here. And this obviously stays there. Now I'm going to multiply through this first part. You kind of have to drag it along with you because that's part of the answer, although you don't have to worry about that because it's already taken that integral, right? It's not under integral. All right, so right now I'm going to say that there are two integrals instead of one. Whenever you have integral of the sum of terms, you can separate that and calculate integral of the sum. If that didn't make sense to you, I'm going to show you where that comes from. You actually use it all the time. Maybe you didn't recognize it, but if you have two functions like this, added, you can always take integral of this function and integral of this function and then add it later, right? You do this all the time. So I'm going to do that here. Remember what we started solving. It's easy to forget after all this. We started solving secant cube x, right? And part of our answer includes exactly what we were trying to solve. So that's not helpful. We're back to square one, right? And I want you to recognize that this is no different than if this was like terms, combine like terms, and then solve it for that, right? That's kind of, treat this as if this was x. If this was x, you would move this side with positive sign, and then you would just solve it, right? It's no different. I'm going to put giant 2 so that really make this point that there are two secant cube x's right now, but they only asked for 1. So I'm going to divide my final answer by 2, and that's easy enough. This term, I'm still dragging this along. And by the way, I didn't kind of explain this. When this minus gets integrated to distributed to both terms, this turns positive. So that's where that positive came from. An integral of secant x, that's ln secant x plus tangent x plus the constant of integration. This integral, as I said in the beginning of this video, you kind of need to know how to take this integral because secant cube gets reduced to taking this integral. This is the only integral that you actually take. Notice that you just did integration by parts, and this is the integral that you take in the end. And that's your final answer, but you have to say 1/2 in front of all the terms, unless you want to divide the whole thing by 2, but that doesn't look good. So I'm gonna do it like this, and this is your final answer. There was one trig substitution in this solution. Knowing where it comes from is also useful. There's obviously knowing derivatives of tangent and secant. You need that to get your v and to get your du. And also rewriting this as secant x times secant square x is another important part. I think that if you don't remember this, it's hard to continue solving it. And yeah, don't forget to turn this into plus, move this with a positive sign, and divide everything by 2.